For a finite line charge, the net electric field at any point on equatorial line makes an angle of dash with the axis of line charge. Okay, so we have a line charge over here, and this point P is on the equatorial point. What does that mean? It means that this line here is the perpendicular bisector of this line charge, which means this distance here and this distance here is going to be the same. Now, in order to solve this question, we can simply use the symmetry argument, which is a very important concept which we should make a note of. Okay, what is the symmetry argument here? Let's say we take a small charge dq over here, okay, and symmetrically we take another charge dq on the opposite side of the equatorial line. Okay, now the electric field due to this charge is going to be in this direction. I'm calling that dE. Okay, and the electric field due to this charge is going to be dE. Why do I say both the electric fields are going to be same in magnitude? Because the magnitude of charge is the same and this distance is also the same. So the magnitude of electric field is going to be the same. Okay, if we say this angle is alpha, then by symmetry this angle is also going to be alpha. Then this angle is also going to be alpha and this angle is also going to be alpha. Okay, now to calculate the net electric field at P, what we can do is we can take components. So here we'll have dE cos alpha and we will have dE sin alpha. So this dE we can get rid of. Here this is going to be dE cos alpha and this is going to be dE sin alpha. So an additional dE sin alpha in the perpendicular direction. Okay, now what do we see? This dE cos alpha and this dE cos alpha is going to cancel each other. So what are we left with? We are left with 2 dE sin alpha in what direction? In the perpendicular direction. Okay, so on any point on the equatorial line, the electric field is going to be perpendicular to the line charge. What does it mean? It means that the angle between the line charge and the net electric field is going to be 90 degree. Absolutely. All right, so let's have a look at the options. So option D is going to be the correct option. For a finite line charge, find the electric field in a direction parallel to the axis of the line charge at point P. So we have a line charge whose length is 7 meter. Now this length BC is given to us as 3 meter. This length is given to us as 3 meter. We want to find the electric field which is parallel to the line charge. Okay, we are interested just in the parallel component. Okay, now some simple calculation here. This angle is alpha, this angle is beta. What is my formula? My formula for E parallel is k lambda by r cos beta minus cos alpha. So obviously I have to calculate cos beta and cos alpha. Not difficult at all. So this angle is alpha. Now this entire length is 7 meter. This length is 3 meter. So this length becomes 4 meter. This length is 3 meter. So using Pythagoras theorem, it's very easy to say this length will become 5 meter. Similarly for beta, this length is 3 meter. This length is also 3 meter. So this length is going to become 3 root 2 meter. Okay, so we have everything. All we need to do is substitute. Alright, so E parallel is equal to K. What is the value of K? 9 into 10 to the power 9. What is the value of lambda? Lambda is 20 nanocoulomb per meter. So 20, but this is nanocoulomb. So 10 to the power minus 9 coulomb. Always use SI units. Divided by R. What is R? R is this perpendicular distance, which is 3. And then we have cos beta. Now, in order to calculate cos beta, what do we need? We need base by hypotenuse. What is base? Base is this line. So this is 3 upon 3 root 2 minus, what is cos alpha? Cos alpha is going to be 3 upon 5. Okay, so all we need to do is calculate this. So this becomes 60, 10 to the power 9 and 10 to the power minus 9 gone. And then we have 3 and 3 gone. So this is 60 multiplied by 1 by root 2. So root 2 I can write it as 1.414 minus 3 upon 5. Okay. So this becomes 60 and 1 upon 1.4. So this is 14 and this is 10. So this becomes decimal and then we have 100 and 14. 7 is going to give me 98. So about 0.7. Okay, so this becomes 0.7 and this is 3 by 5 which will be 0.6. So this is going to be 60 multiplied by 0.1 which is going to be 6 Newton per coulomb. Okay, so obviously we have not calculated it perfectly. it is going to be slightly more than 6 Newton per Coulomb, but approximately this is 6 Newton per Coulomb. The closest answer is 6.4 Newton per Coulomb, and that is going to be my answer. So option D is the correct option. For a finite line charge, find the electric field at the non-axial point P perpendicular to the axis of this charge. Okay, so line charge, this length is 8 meter, length BC is 2 meter, this perpendicular length is 4 meter. We have to calculate the electric field in the perpendicular direction only. Okay, so if we have to do that, obviously the formula we're going to use is E perpendicular is equal to K lambda by R into sine alpha plus sine beta. Okay. Now this angle is alpha, this angle is beta. Again, a little bit of calculation. The entire length is 8 meter, this is 2 meter. So this length AC is going to be 6 meter. Using Pythagoras theorem, 6 meter, 4 meter, this length AP is going to be 2 root 13 meter. Simple Pythagoras theorem. And here also this is 4 meter and 2 meter. Using Pythagoras theorem, we can say this is going to be 2 root 5 meter. Okay, now all we need to do is make the substitution. So E perpendicular is equal to K, which is 9 into 10 to the power 9, into lambda, which is 20 nanocoulomb, again 20 into 10 to the power minus 9, divided by R. What is R? R is 4. Now sine alpha is perpendicular upon hypotenuse. So what is perpendicular here? 6. And what is hypotenuse here? 2 root 13. So 6 upon 2 root 13. Plus we have sine beta. Now sine beta is going to become perpendicular, which is 2 meter, divided by hypotenuse, which is 2 root 5. So 2 upon 2 root 5. Okay. So we have 3 here, and then we have this over here. So this becomes 45. So 10 to the power 9 and 10 to the power minus 9 gone. Now 45 multiplied by 3 upon root 13 plus 1 upon root 5. Okay, so what is root 13? So 3 into 3 is 9 and 4 into 4 is 16. So this is roughly going to be around 3.7, 3.8. Okay, so I'm going to take it as 45 into 3 upon 3.8 plus 1 upon root 5. Root 5 is 2.2. All right, so we have this. Now let's calculate this quickly. So this is 38 and this is 330. So this becomes how many times we can take it? So this is going to be, so let's take it approximately 7 times or 8 times. So 8, 8, 64, and then we have 6 and 24. So approximately 0.8. This comes out to be 0.8. So 45 multiplied by 0.8 plus we have then 22 and 10. So approximately this is going to be something between 4 and 5. So I'm taking it approximately as 5. So this becomes 0.5. So what we have is 45 multiplied by 1.3. Okay, let's do the calculation. 13 into 5 is 65. So 13 into 4 is 52. 52 and 6 is 58. So approximately we have got 58.5 Newton per Coulomb. Let's look at the options. So the closest option we have is 57.6 Newton per Coulomb. So option B is going to be our right option. From a finite line charge, the net electric field at the point P on the equatorial line is equal to. Okay, so we have a finite line charge and we are talking about equatorial point. What does it mean? It means that this line here is going to be a perpendicular bisector of the line charge. Okay, what does it mean? It means that this angle alpha and angle beta are going to be equal. Alright, now by symmetry, we know that this is an equatorial point, which means the parallel components of the electric field are going to cancel each other out because the situation is symmetrical and we are only going to be left with the perpendicular component of the electric field. Alright, so the net electric field is only going to be the perpendicular electric field, and that is given by K lambda by R sine alpha plus sine beta. Okay, now in this triangle APC, we see that tan alpha is equal to 4 upon 4, which is 1. So alpha is equal to how much? 45 degree. So we can say that alpha is equal to beta is equal to 45 degree. Now all we need to do is do the substitution. So E perpendicular is equal to K, which is 9 into 10 to the power 9. Lambda is 10 nanocoulomb per meter, so this has to be 10 into 10 to the power minus 9 divided by R, which is 4. Now sine alpha, sine 45 degrees 1 by root 2. Again sine beta, sine 45 degrees 1 by root 2. So this becomes 10 to the power 9 and 10 to the power minus 9 are gone. So this becomes 9 into 10 divided by 4 multiplied by, this will become root 2. Okay. So what do we have here? Root 2, I can write it as 1.4 approximately. So 10 and 1.4 becomes 14. So we have 2 and we have 7. So 9 into 7 is 63, and 63 divided by 2 is approximately going to give me 31.5 Newton per Coulomb. Okay. Now let's have a look at the options. So the option which is closest to our answer is option B. Hence that is going to be my right option. A finite line charge has minus q uniformly distributed on upper half and plus q uniformly distributed on lower half as shown. Find the direction of electric field at point P. So this is a finite line charge, but the lower half has plus q and the upper half has minus q. And this point is on the equatorial line, which means we can very well make use of symmetry. Okay, how do we make use of symmetry? Let's consider two symmetrical points. So this charge is plus dq, this charge is minus dq. All right. Now this line distance r is the same for both the charges. Okay. So the direction of electric field due to plus dq is going to be this. The direction of electric field due to minus dq is going to be this. Why? Because it is going to be towards the negative charge. Okay. Now let's say if this angle is alpha, then this angle by symmetry is also going to be alpha, which means this angle here is also going to be alpha. Okay. Now what we can do is, in order to find the net electric field, we can take components. Okay. So this dE will become dE cos alpha, and the other dE is also going to become dE cos alpha, and you understand very well what is that going to do. This dE cos alpha and this dE cos alpha is going to get cancelled. Okay. And their vertical components are going to be d sin alpha and d sin alpha. Okay. So the net electric field is going to be in what direction? It is going to be along the y axis as shown in the figure. Okay. So what is my answer? It is going to be along the positive y axis. And now let's have a look at the options. So option C is going to be our right option.